Okay, so far I think we have already seen how do we really see the benefit of FM. So, that is what we started doing. We have already finished discussing about FM bandwidth. Initially people thought it is a bandwidth benefit, we have discarded that, and then we could appreciate the circuits that has to be produced for FM generation and demodulation, and then we started capturing the advantages of FM. Mostly all the channel impairments, probably FM take care of that in a better fashion compared to its AM counterpart. So, that is what we started discussing. We have already given one example where the channel nonlinearity, we have seen that other modulation schemes like amplitude modulation, they are probably not that good to handle channel nonlinearity. Whereas in FM we could see that it can means due to the inherent quality of FM, it can really handle nonlinearity very well. So, that is the sole reason why for high power transmission, where you need to really put class C amplifier which goes into nonlinearity. So, for those kind of transmission, FM was the de facto modulation scheme, because it has a good cancellation mechanism which is inherent to FM. Now, today what we will try to see that in presence of interference, what happens to FM modulation, okay, or what kind of protection it has in presence of interference. So, just to capture that, because the full blown analysis is little bit involved. So, what we will try to see is that as if FM means we are trying to transmit a FM which is either a constant thing or it does not have any modulation, it is just the carrier we are transmitting. But of course, you will see the essence of the cancellation is already means that will be understood through this analysis. So, what we will say? We will say unmodulated carrier A cos omega c t is being transmitted. So, of course, if it is FM modulated, so there should be some phase term which is for FM it will be an integral of m alpha d alpha into kf, or Pm it will be just mt into kp probably. So, there should be a phase term, we are just neglecting that. That means unmodulated, just the carrier we are sending. Okay. So, there should be a phase term, we are just neglecting it for our purpose of analysis, and you will see that it is not that much required, because at the demodulation we will still employ FM demodulation. So, and we will get some insight. So, let us say this is the desired carrier, and nearby that we have some interferer which has a strength of I, and it is nearby. So, the frequency is omega c plus omega t. Okay. So, it is just this is the carrier frequency, let us say at omega c, and there is nearby some strength I, this is having strength at omega c plus omega. So, that is the interferer actually, and we have to see what is the effect of this interference and what FM does with this interference. So, that is something we wish to check. So, basically what will happen, suppose my received signal will be, because in channel I will have this carrier as well as this interferer. So, it will be addition of these two, right. So, I will have A cos omega c t plus I cos omega c plus omega t. This is what I will be getting. I can just open this cos omega c plus omega, and then I will be getting A plus I cos omega t into cos omega c t, just a algebraic manipulation, minus I sin omega t into sin omega c t, right. This is what I will be getting at the FM, and we are thinking that this I is close enough in the band pass filtering zone of FM. So, basically it is an interferer which is within the band. So, it will not be cancelled by the filter. So, it will still be inside, and we want to see those are the valid interferer, and we want to see what is the effect of that interference into the FM modulated signal. So, this is what we are trying to analyze. Okay. So, this can be written as, because it is cos omega c sin omega c, and this can be represented in a overall cosinusoidal with an envelope and a composite phase. okay, where of course this ERT should be this square plus this square and square root, and we are interested in phase because FM demodulator will actually detect this phase and differentiate it, right. So, this phase will be, that must be tan inverse, as we know, this divided by this whole thing. So, this divided by this. So, that should be I sin omega t divided by A plus I cos omega t. Now, if it is an interferer within the band, we expect that the interference probably will be smaller in strength, because if interference is almost of similar strength with the signal itself, probably nobody can do anything with that, it will still be present. So, we will assume that because it is interference, so of course, A must be much greater than I. Okay, so, this is the interference. In picture also we have almost demonstrated similar thing. So, if that is the case, then I see, because it is I cos omega t, this will never be bigger than I. So, this can be neglected compared to A, and then this will be, so this becomes tan inverse I sin omega t divided by A. Again I by A, that is a very small number. So, this can still be approximated. So, these are all approximation. So, tan inverse theta will be just tan theta I sin omega t divided by theta, right. So, that is becoming my phase, the FM overall FM phase. Okay. So, FM modulated signal and the phase part of that. So, when we demodulate it, what do? We take the phase and we actually differentiate it, whatever we get, that should be, sorry, that is not theta, that should be A. So, we differentiate it, that will be the frequency, and that must be my signal. That is how FM demodulation goes. It detects the phase and then differentiate it to get this, right. So, that we have already understood, because in the phase it will be integration, and then you differentiate it, you get the overall phase. So, here also, because it is a FM demodulation change, so we will be employing same thing. So, this particular phase will be differentiating, and whatever we will be getting, that is my received signal. Okay. So, what we can say that d dt of phi dt, let us call that as y dt, that must be the demodulated signal. So, that must be, so d dt of phi d, whatever we have calculated, that approximate value I sin omega t divided by A. Okay. So, if I differentiate it, it will be I omega divided by A cos omega t, right. This is what we get. So, basically we have, what we have done, we have tried to see the interference. We have just said that we are probably transmitting a FM signal, but we are just considering its unmodulated FM, that means just the carrier, we are just for testing purpose, just the carrier we are sending, and nearby that carrier within the band of FM I have a interferer which is at omega c plus omega. Okay. So, these two signal are in composite falling in my receiver. I am just trying to detect the phase the way FM will be doing, and phase, if you differentiate, that should be the frequency variation, and that we call as a detection. Okay. So, this is what I will be detecting, right. So, that is my phase, and now let us see what happens. Okay. If I just try to plot, so this is actually, see, actual my FM modulated one was having nothing. So, in the detection I should get a 0 thing, okay. So, because there was no modulation, so it must be a 0. So, it should be getting 0, but it is getting this thing. So, that is my interference in this case, interference getting transformed after doing means FM demodulation. So, what is that? Let us try to see that. First of all, there is a factor of I by A. Okay. So, we have already said if A is bigger than I, so there is already means the interference is becoming A times lesser. Okay. So, when it is interfering with FM, because of FM demodulation process, it is already becoming A times lesser. As long A is higher, probably it will be already lesser, that is one thing. Second thing is, it is getting multiplied with omega. So, if you see that omega is the separation, right. So, if I just plot it with respect to my frequency omega and then try to plot this interference, how it will be at omega equal to 0, it is 0 and then there is a linear curve. Okay. So, of course, you can always say that there is a cos omega t term, but okay, if this cos omega t, and because I do not plot it with respect to t, I will take the probably worst case scenario. So, what is the highest value of this? This is 1. So, it will be just I omega by a. So, I am plotting the highest value of interference, that is what we are interested in, that how much interference at the peak will be coming to me. So, that at most will be this, which is I by a into omega. So, it goes linear with omega. So, this is the interference. Here remember, deliberately we have taken out the signal. So, we should expect after FM demodulation 0, nothing, but we are getting something and we are calling that as interference. So, that was just to make the overall analysis simplified. If you give FM, then there will be more involved term. So, we just wanted to simplify that. We are just capturing the interference effect. So, what we can see that as omega is closer, this is a very interesting thing, the interference term is smaller. So, as the interfering signal comes closer to you, you are more afraid that because the interference is closer, probably more interference I will be getting, but FM has a cancellation part. Okay. Due to its modulation and demodulation, it cancels that. So, basically if the interferer is closer to it, it overrides it in a better fashion. As the interferer goes away from it, of course, within the band of FM, if it goes beyond that, your filter will cancel it, but within the band of it, if it goes little farther, probably little bit more interference will be coming to you. Okay. So, this is what will be happening. So, what we can see already that FM has a nice cancellation property of interferer. So, any interference that is coming in the band of FM, closer it is with the FM carrier, more it will be cancelled. Not only that, it also gets overridden by the carrier strength. So, if the carrier strength is enough, the interferer, if that is much smaller than that, so overall worst case interference will already be overridden by this FM. So, this is particularly termed as capture effect. This is called as capture effect of FM. So, that means what it does, actual FM signal if you transmit, that is your desired signal. So, whenever you are demodulating, it will actually have a overriding factor over all the close by interferers. So, it captures that and actually exert more power in terms of demodulated output. Okay. So, that is a very good property because we want that, we want interference cancellation, and FM automatically due to its demodulation, inherent demodulation technique, it cancels them out. That is a very nice property. So, what people have seen over here that in AM, if there is a nearby interferer, that must be almost 35 dB less, then only you get proper signal to interference ratio. Okay. Whereas for FM, you can go as far up to 6 dB less. Okay. So, that is a big advantage. So, almost 29 dB extra interference, still you are good enough, almost both the receivers will behave equivalently. So, that is the advantage of FM we were talking about. That FM we have now shown two advantages. One was already with the nonlinear channel, that FM cancels it out very nicely due to its inherent demodulation and modulation technique. And now we could show that if there are interferer even within the band, FM actually overrides them, which is called termed as capture effect, and it means gives huge advantage over the interferers whenever you are transmitting FM. So, next what we will try to do is we will try to show another big advantage of FM, that is the noise cancellation, which is almost similar to this part, but probably the analysis will be little more involved. So, we will try to capture the overall overall noise effect in FM. Okay. So, for that we will go back to our noise analysis in similar fashion. So, what we did in our noise analysis, it was a simple thing. We have drawn the receiver transmitter module and then we means for AM analysis also we have done always try to capture the figure of merit. What does that means? If I recollect, that means that if you transmit the same signal in same or insert or put same amount of power as you are putting in FM in the baseband and try to see what is the performance. So, this is the benchmarking one, that is the reference one. Try to see if I do not do FM, I just insert same amount of power that FM has to put, okay, FM modulated signal has to put. So, I put the same amount of power and try to see what is the performance if I just transmit it in baseband without doing any modulation, and on the other side any demodulation, only that filtering will be there, low pass filtering. So, with that we get a reference SNR, okay. And then what we do with the same power, because now the powers are equivalent. So, we actually transmit the FM modulated signal, and then in the channel as expected noise will be added. After that the entire demodulation of FM will go on, then we will get probably the signal and noise will go through this demodulation process, and finally we will get some expression for signal and noise, and that will be the actual signal to noise ratio if we get the power of these two. And then after FM demodulation we try to see what is the SNR, and then we compare these two SNR, compare to the reference SNR how better or how worse this is, and that gives us a ratio which is called the figure of merit. So, we have already calculated evaluated figure of merit for AM modulation, DSBSC, SSB, SC. So, we have done all those things, and we could see that they are DSBSC and SSBSC, they are having figure of merit 1. That means, it has no advantage with respect to equivalent baseband transmission, whereas AM was even worse. It means with the tone modulation we have proven that the highest it can get is 1/3, okay. It will be always less than that. So, now we will try to see with FM what happens, okay. So, let us first try to draw the receiver chain, that is the first task probably. So, I have FM, that is the summation, this is the channel. So, basically FM modulated signal I will be putting over here, which is my signal, which is just FM modulated signal. That means I can write it as AC cos omega c t plus kf if it is represented in omega domain, and 2 pi kf if it is represented in f domain, okay. So, accordingly kf minus infinity to t m alpha d alpha, that is it, okay. So, this has an equivalent representation if I do it for frequency domain. So, I can write it AC cos 2 pi f c t plus instead of kf let us call this as kf dash. So, here we will be writing 2 pi kf. So, this is in frequency domain or f domain we should call, and this is in angular frequency domain, omega domain, okay. So, that is my FM. So, this is what will be inserted over here, and from here in the channel there will be noise which will be added over here, right. And after that, after the channel the FM demodulation starts. So, the first part of demodulation should always be a band pass filter. So, this is the band pass filter of FM. Now, this band pass filter is no way related to just the frequency of the modulating signal, it is the FM band, okay. So, we call that as from minus Bt by 2 to plus Bt by 2. So, Bt is the overall FM band suppose, which comes from the Curson's formula, okay. So, we take that, it has a part of del f, it has a part of B. So, it is actually 2 into del f plus B, right. So, that is what we have understood. So, this is that particular part, okay. So, that band pass filter should be put so that the entire FM band comes into my receiver. After that, so we call this signal as xt, okay. This should have noise part as well as the FM modulated signal. After that, what we will be putting? We will be putting a FM demodulation. So, the simplest one we know is a differentiator followed by a envelope detector, right. That is one of the FM demodulator we have seen, it is just you differentiate it, the entire frequency variation comes into amplitude as well, and then you do envelope detection. We have already proven in the last class that with envelope detection we will be always getting our signal back, right. So, that is the whole purpose of this is probably the main part of FM demodulation. Okay. So, after that let us say we get a VT. After this in FM demodulation, this will be clearly understood from the noise analysis that we need to also employ a low pass filtering. You will see that later on why that is required. So, this low pass filter is just of the message signal band. So, that goes from minus W to plus W, and after this we get an output. Okay. This low pass filter will just facilitate us in terms of noise cancellation, and you will see that FM only gives this facility, all other modulation scheme does not give this facility, and that along with some other things which we will be exploring gives the FM edge over other modulation scheme. So, we will come to that. Okay. So, this is the overall receiver architecture, right. So, let us see how the demodulation happens. So, I have a signal which is ST of course, but I also have a noise which is band pass noise. So, I can always write it in terms of in phase and quadrature component. So, I can write it as NIT cos 2 pi FCT. Here I can means the representation does not depend on whether I write plus or minus. So, I can take any one of them. So, for our advantage which will be clear in the next phase of derivation, we take minus. So, it is equivalent, it is just a representation whether you take plus or minus, spectrum wise there is no difference, okay. And representation wise also there is no difference. Okay. So, this can be written because the central frequency of my band pass filter is this Fc. Therefore, this amount of noise which is from minus Bt to plus Bt over that band, or minus Bt by 2 to plus Bt by 2, that means Bt, that is the FM bandwidth. Over that band the overall noise will be coming through the receiver, and that is the band pass representation of that particular signal. Okay. This can further be written as RT, as any summation or addition or subtraction of two sinusoidal can be represented as another sinusoidal. So, this can be written as RT cos 2 pi FCT plus psi t, right. So, this is something I can write, where of course RT you know already, it should be root over NIT square plus NQT square, that is the RT, and psi t must be tan inverse this divided by this. So, it should be NQ okay. So, as long as these two Ni and Nq, we have probably not talked about these part, and due to time constraint probably we will not be able to prove that, but this is a very important derivation in random process, that if these two we have already proven that they are independent. Okay. So, that is something we have proven, in fact we have proven they are orthogonal also. So, as long as that is happening and they are Gaussian, okay, so that is something if we assume generally that is what happens, then we can always prove that this RT actually follows a Rayleigh distribution. So, this is something which will be can be proven. I am not going into the details of that because that will means take us to somewhere else. So, due to time constraint we are just taking that. So, it is a Rayleigh distributed one, and the corresponding psi t also can be proven that that is uniformly distributed between 0 to 2 pi. Okay. So, this is something which will be happening in a random process. So, these are also a separate random process which follows like this Ni and Nq or overall Nt, that follows a Gaussian distribution. It can be proven that these are also random process which follows, this follows Rayleigh distribution, this follows a uniform distribution between 0 to 2 pi. Okay. So, that something can be proven. So, we are just leaving it over here, but probably you will see that is not that much required for our derivation. Okay. So, anyway we have got this. So, immediately what we can write is Our ST, that is something we know already, it is AC cos 2 pi FCT, that is the transmitted one, plus 2 pi KF in terms of frequency if we represent minus infinity to T m alpha d alpha. So, that is the FM modulated signal. Okay. So, overall signal, that is XT after the band pass filter, will be this ST plus NT, right. So, ST happens to be AC cos 2 pi FCT plus 2 pi KF integration minus infinity to T m alpha d alpha. So, this is the part, and the noise also has its equivalent representation, which I can write as RT cos 2 pi FCT plus psi t. Okay. That is how we have represented the noise, that is the after the band pass filter. So, this is a band pass noise and this is the actual FM, because FM, the band pass filter just exactly allows the entire FM signal. So, FM signal remains undisturbed. Okay. So, this is what we get after the band pass filter. Now, what we will have to do is, next we have to see if this is the signal plus noise, what my discriminator will do. Okay. Or probably I have not given that term. So, this entire part, that differentiation followed by envelope detection, that is called, termed as discriminator in FM demodulation. So, that is called overall a discriminator circuit. So, what this entire circuit will do, that is something we have to see, because earlier whatever we have seen, that was easier, because we are directly differentiating this term, but now we have the noise, which is a random process again. So, therefore, that direct differentiation will not work probably, we have to do it means borrowing the theory of a random process. Okay. So, that is something we will have to do, and equivalently we will have to calculate the overall power spectral density of the noise that we get after the discriminator. That will be the next task that we will have to do to analyze the FM in presence of noise. Okay. So, in the next class probably we will discuss in details how we can analyze FM in presence of noise. Okay. Thank you.